Swayam Prabha. Digital India. Educated India.
So this is kind of the summarization of the communication part of it, which is the comparison of the methods. As you can see here, here in this particular case, you have on the left hand side GPU 1 and 2, and you're using data parallelism. And as you can see, you are basically passing it as in different data, but the same set of layers exist in both the GPUs. And at every level, what you're trying to do actually is you are averaging the gradient. So you are basically communicating the gradients across and then finally averaging them. On the right hand side, what you see is the model itself, where you will have you are exchanging slightly different things, right? So you are exchanging the activations, and you are basically the communication is of different type. You are basically not averaging, but you are actually exchanging the activations, and the communication pattern is slightly different, or actually it is much more different. The reason to understand this will also be explained in the next couple of slides for you. So I was also referring to you in the terms of synchronous and asynchronous communication. So we will be focusing primarily on the data parallel approach in our in the couple of lectures that we are doing. But within that also you have two types, synchronous and asynchronous. On the left hand side, what you're seeing is the synchronous approach, and as the name suggests, the synchronous approach is an approach where all the workers are kept in sync, which means every worker is in sync and they know the status and the values of the other workers, and in the every step to make sure that they apply individual updates to the model, and all of them at any point of time have the same copy of the model. This is very important aspect of the synchronous communication. While in the asynchronous data parallel approach, the workers basically obtain the variables from a parameter server. So you can see there is one more component which has got added, which is called as a server. As the name you might have heard, the server is basically responsible for talking and giving updates to all the different basically clients. Who are the clients here in this particular case? The clients are the workers or the GPUs themselves. And basically the workers obtain the variables from the parameter server and store the results back after processing. The parameter server would apply those updates and update the variables. This allows the workers to work independently. Now this is very critical. If you see on the left hand side, especially in the synchronous communication approach, since every worker needs to be in sync with the other workers, they are always going to go in a step-by-step manner. So even if one worker is lagging behind, it will affect the scalability of all the other workers, because they have to wait till the time all the workers are at the same state. So in case of load imbalance, or if one worker is slower as compared to the other, you can get into scaling issues. While in case of asynchronous communication with parameter server, the workers actually work independently of each other. And we are going to, in the next set of slides, we are going to focus on the synchronous data parallel approach. But asynchronous has its own way, and it kind of finds its own space to make the scaling go better. But no matter what we talked about so far, we talked about either using synchronous communication or using asynchronous communication, using data parallelism or model parallelism, and how to split that and everything. What is one thing which is common across all of them is communication. You need to communicate. The workers needs to communicate either with each other or with the parameter server and at what level? Are you going to do averaging with each and every worker? Are you going to do activation, communication? So whatever is the approach that you're going to follow, it is going to be dependent on the machine and how GPUs are connected to each other and how the machines are connected to each other, because finally the communication is going to define if you can scale it or not. So what matters is, in this case, is the system topology. In the networking world, or in the system, in this computer architecture world, the definition of it is called a system topology. So when I talk about topology within a node, how are these GPUs connected to each other? Across the nodes, how are these two nodes connected to each other? How are the GPUs connected to the interconnect? All of these is basically going to define the performance or the scaling of your model. And that's what we are going to look at in this next couple of slides. So if I look at this particular example here, what you're seeing is an example of a system topology where you have a system which is having something called as the NV switch, right? So you are seeing here, this is a baseline version, and this is the version which is of a particular server which is referred to as NVIDIA DGX2. Now, what you're seeing is in the system config, in the first one, the baseline consists of a server which is of type DGX1. DGX1 is another server. This DGX1 basically has 8 GPUs. So you have basically 8 GPUs, and what you're doing is, in the baseline version, is basically that you have two nodes, which is two DGXs connected to each other via a interconnect like InfiniBand interconnects. In this case, the InfiniBand type is also given, right? Versus I am having a node which has 16 GPUs. So instead of going across nodes, I am within the node, and within the node I am using a specialized switch which is called as NV switch. And when I don't go across and within the node, you can see here that the amount of performance gain that you can get over the baseline version is much higher. So if your baseline version is this, you can get up to 2.5x speed up by using a network topology of a machine which can do faster communication with a lower latency, and we are going to talk about that in a bit. So you can get a large amount of difference based on the machine which you are running it on. So one concept that we need to understand is the definition of throughput and latency. And it is very important to understand it, because it's not just about how much speed network I have in terms of bandwidth, but also latency matters a lot, right? Because if you would have seen in the previous set of slides, the communication is happening quite frequently. Now, the gradients are actually maybe very small. So you don't need a network which is having very high bandwidth, but you might require a network which is having very low latency. So one concept that we are going to look at is this. So latency is the time taken for the transfer of a single packet of data, which means if I were to just send, if I just were to go from here to the airport alone, right? So if based on the kind of a bus or whatever method I use, I can reach faster or slower. I'm not confined with, say, the number of people who are going to go with me. So it's like latency. So whenever you are testing your networks, if you do a speed test of your network, you always get two numbers. Latency would be given in terms of how many milliseconds or microsecond it takes to do a ping. So it's the ping latency, right? In this case, we are talking about the latency of the data being sent from one place to the other. The throughput is basically measuring the amount of data that can be transferred in one unit of time. Like, can I transfer 10 of them together in one shot? Can I transfer 1 KB of data, 1 MB of data, or much more amount of data? So how much can I transfer in one shot? So these are two different things, and they are kind of related to each other. They are basically related by equation that you see there, right? The throughput is basically nothing but the bus width divided by the latency. Interconnect is the way the two systems are connected. So basically the two systems are connected to each other via one or the other form of interconnects. For example, the two systems may be connected via LAN, which is your normal Ethernet, or they can be connected to each other via, say, a PCI bus. If they are within the same node, two GPUs can be connected within the node using some other interconnect called as PCIe. To give you an example of our latest generation architectures like A100, A100 basically has a specialized interconnect which is called as NVLink. If you look at the Ampere cards which are present in the latest generation, they have a particular interconnect called as NVLink, and this is a third generation NVLink. And you can see here that each and every so you get up to 50 gigabit per second per signal pair. So you have different number of signals, and you can get up to 50 gigabit per second per signal pair, and you have 12 of them, right? So if you divide it by 2, because you can do both in and out in parallel, so you basically have 12 links which can run at in and out speed of 25 gigabytes per second. A total amount which comes to is 600 gigabytes per second of total, which is twice more than a previous generation, which was V100. So based on the type of GPU you are going to use, the communication across and the NVLink bandwidth, or sometimes you might be using, like if you use the free instances on the Google Cloud or the other instances out there, it does not even have a NVLink. And when you start using multiple GPUs, you may not get the scaling that you expect out of it, because it does not have this specialized network protocol which is there in A100 called as NVLink. And based on the types of system topology that you have, you may or may not have these kinds of features. Like in here, we are talking about a feature called a GPU Direct. What the GPU Direct basically means is that if one GPU is connected to the other GPU in a friendly peer-to-peer manner, or which can allow GPU Direct, the GPUs can directly talk to each other, which means one GPU can directly transfer the data to the other GPU, and it does not need to depend on any other thing to do the transfer. That kind of matters, and it is dependent completely on the kind of system that you are having GPU in. The other method is also the communication concept, which I was showing some time to you, right? So the communication interconnect, in the previous slide that I showed you, we noticed some basic terminologies that happen in an interconnect, right? We can also have multiple types of interconnects. Like on the left hand side, you are seeing a method which is called as a host staging. The data which is being transferred from different GPUs, the data is traversing from GPU 0, as you can see here, it is traversing via the PCIe bus to the CPU first, and then from the CPU it is staged in a buffer before being copied into GPU 1, right? So based on the type of system topology or the method that you have, you are going to basically have these things, right? Whereas if you see the second method, if the GPU Direct was enabled, and if you're using a better system topology in the peer-to-peer communication approach, they can directly be connected via interconnect. Right here, you can see here the interconnect is PCI switch, and GPU 0 is directly talking to the other GPU via the PCI switch. Or it can use the NVLink protocol that I just talked to you about, directly using much more higher bandwidth and lower latency as compared to using a PCI switch. Now, why am I telling this? Because some of the numbers which I am showing you, based on the kind of hardware that you use, based on the kind of network topology or the kind of system you have, you will get different performance numbers. So here you can see the system topology. Now the question you might ask is, how do I know what kind of a system topology I have? The good thing is, if on the when you install the NVIDIA drivers, you can use this particular command here. Like in this case, it has NVIDIA-SMI topo-m. This NVIDIA-SMI topo-m. Topo is topology, -m stands for matrix format. So you can see here, this is a particular output of a system which is DGX1. What it is showing you is from GPU 0 to GPU 7, and then it also has the InfiniBand adapters of Mellanox, 4 of them. And then if I were to go from GPU 0 to GPU 0, it is X, because I'm within the same GPU. But if I were to talk from GPU 0 or transfer the data from GPU 0 to GPU 1, I can use NV1. NV1 is what? It is nothing but NVLink, which sorry, it is the NVLink 1, right? Same, in GPU 0 to GPU 2, I can use NVLink, and you can see I can use NVLink from GPU 0 to GPU 4. But when I want to talk from GPU 0 to GPU 5, it says that the communication protocol is SYS. What does SYS mean? It is connecting or traversing PCI as well as SMP interconnect, which means it's going to basically do the host staging. So it's going to take the larger part, the lower bandwidth part, the higher latency part, and the CPU comes into the picture, resulting into really low performance between GPU 0 to GPU 5, 6, and 7. Now that's how the overall topology can be found out very efficiently. Network topologies which don't have a really good interconnect pattern, they may result into not so much of good performance numbers when you're trying to scale across. So you can use this command NVIDIA-SMI topo-m to see the network topology. So this is the topology that I was talking to you about, which is there in DGX1. You can see here that there are two CPUs. Both the CPUs have PCI switch. Via the PCI switch, so the CPUs and GPUs are connected to each other via the PCI bus. And within the GPUs, so you have, like here you can see here, you have total 8 GPUs, and the GPUs are connected to each other via also the NVLink. So you can see here, these ones are the NVLink protocols, while these ones are the PCI buses, right? So as I was showing you some time back, I said from GPU 0 to GPU 5, you can see here there is no NVLink. That's why it has to go from here to PCI, then to CPU, and then come to GPU 5. Now you can see here that this is what I was just trying to show you previously in the NVIDIA-SMI topo-m. So why does it matter for us, right? Now that's what we will see in this particular slide, where when we are trying to do this communication, how does it matter? Suppose if you had a system where you had just PCI bus, you didn't have NVLink. So if you remember, there are different kinds of communications which are happening. So the first thing you're going to do is that you're going to load the data from the file system to GPU to the CPU to the GPU. So you're basically doing the data loading over the PCI bus. So you load from file to CPU to PCI to the GPU. And when you are running it in parallel, you are also doing at the same time gradient averaging, and that also you will do via the PCI. So you're using the same PCI for reading the data or transferring the data to the GPU, and also you are using it for the gradient averaging part, which will basically result into choking of the PCI bus alone, right? So the data loading and gradient averaging are basically sharing the same communication resources, leading into congestion, right? What if you had a different system and that system basically had NVLink inside it? In that particular case, you can basically do this, that the data loading actually happens while the PCIe bus from the CPU taking this particular path, while the gradient averaging can basically happen via the NVLink. So the GPUs can talk to each other via the NVLink rather than via the PCI, same PCI bus which is being used for the data transfer as well. So there is no sharing of communication happening across the resources, and hence resulting into almost no congestion and resulting into much more better scaling, as I would say, or the performance part of it. Now, the question you might ask is, should I worry about it? Should I not worry about it? It's always a good idea to look at a system and then understand on whether you are going to get good scaling or not. But from a point of view of the frameworks like PyTorch, TensorFlow, and all of them, they basically take care of all of this communication behind the scenes for you. But you might or might not get good performance. But NVIDIA has provided libraries which can result into better performance. It tries to find a lot of things like all of your frameworks like PyTorch, TensorFlow, and all. They use our library when you activate multi-GPU computation. So a library called as NVIDIA Collective Communication Library, or NCCL. Basically, NCCL is a library which provides you many things. It provides you fast multi-GPU and multi-node communication. So it provides you fast collective communication routines for multi-GPU, multi-node acceleration. NCCL improves the application performance by maximizing inter-GPU bandwidth utilization. And also it is very easy to integrate or optimize for high bandwidth kind of networks. And it is basically integrated into all of the major deep learning frameworks like Caffe, Microsoft Cognitive Toolkit, MXNet, PyTorch, TensorFlow, and all. So you can see here it enables multi-GPU NVLink or PCI based. It enables multi-node InfiniBand based topology. It also does automatic topology detection. So let me just take you to another slide. So as I was saying that basically NCCL provides a lot of things. It does a lot of behind the scene things, like the first thing that it will do is to do topology detection. What it does is it looks at the overall system. It builds a graph including where all our GPUs, NIC cards, InfiniBand cards, CPUs, should I be traversing PCI switch, or does it have NVLink, or does it have NV switch? So it does a topology injection for different settings. It does a graph extensive search to find the optimal set of rings or trees. So it tries to find what is the best traversal path. It does a graph traversal and tries to find the best path whenever you want to communicate across. And it does the graph connection based on that, right? And finally, then it runs all of this. The communication happens not by the CPU, but it actually runs inside the GPU as small GPU kernels, and the CPU threads are basically for network communication. So it uses a smaller amount of GPU for basically doing these kinds of things. So you can see here, it does a lot of things behind the scene for you so that you don't have to worry about it. The only thing is, if you have a system which has better system topology, it will help you in doing it. So if I were to use NCCL separately, not within these frameworks, it basically does something like this. You will write a code like, first is to create a unique ID or the communicator. You're going to create communicator, and then you are going to do different communications in forms of like NCCL send or receive, or you can do collective communications like all reduce, broadcast, which are particularly very well known in the MPI world. But the good thing is, basically all of these frameworks behind the scene, whenever you want to do this gradient calculate averaging across and you want to communicate, all of this code has been written behind the scenes so that you don't have to worry about this. But the library NCCL is in general present, and you can utilize it if needed. And as I said, all of these frameworks, TensorFlow, Harvard, MXNet, PyTorch, all of them are, it is important to know that how this framework basically implement this, and each of them have a different basically a way of using multiple GPUs, and they call it as strategy. Like in PyTorch, you will have torch.distributed. It has three main components, while in Horoword is a very popular distributed framework that works with TensorFlow and PyTorch or MXNet. It's a completely different framework. And as we had shown you previously also, all of this is present on our NGC. So NGC, as you remember some time back, NVIDIA GPU Cloud, all of these containers supporting multi-GPU and the right version of NCCL and all are contained into one particular unit. If you do it manually, it is very, very error prone. So rather than that, you can actually use the NGC and make sure that you have all the dependencies which are set. So with that, I am done with this session today. Today, what we covered was the requirement of how to use multiple GPUs. What are the effect of using multiple GPUs when you have different kinds of systems, and also how you can check the different parameters.